So let's start from the foundation, the Lotka Volterra model, prey-predator model, the model that took name from Alfred Lotka and Vito Volterra, which in the 20s, basically during the same time, converged defining these dynamics between prey and predators. The assumption here is that prey grows exponentially in an absence of the predator, and the predator also dies exponentially in the absence of prey where to feed upon. The other assumption is that there is no density dependence regulating the prey or the predator, so the prey has an exponential growth and would grow indefinitely without a predator. And the predator, of course, depend upon the prey, but there is no density-dependent relationship that regulates its own mortality, for instance. And the other assumption is that the probability of encountering of a prey and the predator is actually depending, is random and depend upon the abundance of the prey and the abundance of the predator. So this is the model that you can see here. It's a model of two equations. One describes the dynamics of the abundance or the biomass of the prey that is here described by n as a state variable, and so dn over dt is the rate of change of the prey population, and then the abundance of the predators, p, where dp over dt is the abundance of the predator. As you can see there, the prey in the absence of the predator will grow exponentially with an instantaneous per capita growth rate equal to r. Okay, and the predator will die exponentially with an instantaneous per capita mortality rate equal to mu. Okay, but when the prey and the predators are in the same basically environment, then every encounter between a prey and the predator might translate into a predator successfully attacking the prey. So the probability of encountering is here assumed to be proportional to the abundance of prey and predator. Okay, that's why n and p, and proportionally to a coefficient q, which is a predation coefficient, which is an aggregated coefficient that account for the mobility of the prey, the mobility of the predator, you know, whether the prey is crafty or not, whether there are refugees. There are a number of factors that are all subsumed into this coefficient, which we have referred to here as q. There is another element that is important here, as you can see, that is then whenever a predator successfully attack a prey, you know, we need to account for the ecological efficiency. So the conversion for the prey basically to the predator, which is here described with the letter E, the ecological efficiency. In terms of biomass, just to mention, the typical, you know, ballpark numbers is around 10% of ecological efficiency. So when we run simulation, you can see here that, sorry about that, is that we see that starting from arbitrary initial conditions in arbitrary time units, we see that there is this oscillatory dynamics. The prey initially increases exponentially, but eventually the predator catch up and reach a density or abundance that is sufficient to keep, basically to prevent the prey to continue to grow exponentially. In these specific cases, it actually collapses to really low number. The numbers at some point are so low that the predator is unable to sustain, you know, itself, the population, and so the population of the predator cells slowly decline. Okay, and eventually there's so few predator that the prey has another burst and growth exponentially before collapsing again. Okay. So this is really interesting. And if we start from different initial conditions, you know, we basically get the same type of outcome. That's mean oscillatory dynamic. The prey initially growing exponentially, but the predator catching up, okay, and then eventually controlling the, you know, the prey abundance. So what we learn here from this exercise is that a predator is able to control a prey that otherwise would grow exponentially. It's very interesting. And then we also see that the system gives rise to oscillatory dynamics, produces oscillatory dynamics, which is also very interesting. One thing that is actually, kind of the unsettling here is that, as you can see from the two panel here, that depending upon the initial conditions, we basically get dynamics that are really looks alike among themselves. But the peak, for instance, of the prey in the lower panel is about 600, in the upper panel is 1500. And the period of oscillations between two peaks is definitely shorter in the lower panel than in the upper panel. So there is something, depending upon the initial condition, that is a little bit upsetting, because we get slightly different numerical results depending upon where we're starting from, which, might be just an inherent feature of the system as it is represented by this dynamical model. But one point that is interesting is, we saw what the model tells us, the predator will be able to control a Malthusian prey, basically. But then about the equilibria, how many there are and what type, this is what we want to see. There are several ways of doing that. We will summarize that in just a few slides, but I would say one way that we can see that here is by using basically the method of looking at the isocline in the phase plan. That is the plan where we, for instance, draw the number of predators on the horizontal axis and the number of predators on the vertical axis, and then we look where in this plan the rate of change of prey or the rate of change of predator in time is equal to 0. What does it mean? We'll see that here. Let's assume dn over dt, which is equal to Rn, the exponential growth, minus the predation. Let's assume that we set this equal to 0. We want to see for what values of n and p, this equation is equal to 0. And this is pretty easy to say, because we can set n equal to 0 and multiply both the denda there. And so if n is equal to 0, dn over dt will be equal to 0, which is good. That means that if we have no prey, there's not going to be any prey. There's no immigration in this type of model. But we can plot this here. So that n equal to 0 is basically the equation of the vertical axis. The other value for which that dn over dt is equal to 0 when p is equal to r divided by q. If p is equal to r divided by q, then dn over dt is equal to 0. And we can draw this as a basically straight horizontal line that intersects the vertical axis, as you can see, for r divided by p. We can do now the same exercise when basically dp over dt is equal to 0. So we set this equal to 0, and this is equal to 0 when either p is equal to 0, which is the horizontal axis, basically, or when n is equal to mu divided by eq, which is the equation of a straight line that intersects the horizontal axis, as you can see here, when n is equal to mu divided by eq. Equilibria are given by the intersections of prey isocline with the predator isocline, as you can see here. And so let me just draw them all here. And so we plot, the green isocline of the prey along with the red isocline of the predator. And we see that indeed there are actually two intersections in this specific case. One is the trivial one, 0 prey, 0 predator, which is okay, and and the other one is when n is equal to mu divided by q, and when p is equal to r divided by q. So this would be a coexistent equilibrium. Okay. The other things that we know is that because of the way we draw this isocline, dp over dt, which is the p dot represented there, is set equal to 0. So if anything changes there, is now p, only n can change. So very close to the basically, or on the horizontal axis, if we have no predators and only prey, well, we know that the prey will grow exponentially, so well, the number will increase from left to right. Okay, and over that, red isocline where dp over det is equal to 0. Again, p cannot change, its rate of change on that line is equal to 0. The only thing that can change is n, the number of preys, and number of preys, we can show that it's going to increase. And likewise, on the vertical axis, where we have no prey, only predator, well, the predator will die of starvation, and so will decrease exponentially down, to basically local extinctions. And if we move out from the axis, as you described here, we basically know that on the isocline of the prey, basically there, for the way we have derived, the prey cannot change by definition. This is how we derive it. So if anything changes, is the number of predators. And so whatever trajectories that are going to be there, they're going to intersect the isocline of the prey, the green line, with infinite slope, and the isocline of the predator, which is the red lines there, with a slope that is equal to 0. So with where the tangent basically needs to be, horizontal on the red line and vertical on the green line. The obvious following question is whether this equilibrium of coexistent is stable, is unstable, a repulsor, or neutral, right? So if, for instance, we might assume that prey and predator will oscillate and maybe spiral down to that coexistent point, which would be an attractor in that specific case, or could be spiral out, in that case would be a repulsor. There is another case which is represented here, in which we might have sustained cycles that do not explode to infinite, but they also do not die off. Okay, and as we mentioned, the only precise way we can do that, we can infer that from the isocline. Actually, if you have good eyes, you can understand it, but you can do either by numerical simulation or analytically by linearizing the system around the investigated equilibrium and computing the corresponding eigenvalues. Okay, so we saw here, and I'm going to repeat it there, how we did the graphical analysis by deriving the isocline, drawing, finding the intercept, and trying to infer whether those equilibria are stable or unstable. The formal analysis, for which we do have some R script that show how to do that, it's really linearizing the system, which in this case, it means we're going to compute a 2 by 2 Jacobian matrix of the linearized system that is of S corresponding to the specific equilibrium, the trivial one or the consistent one, and computing the corresponding eigenvalues and determining whether the real part of the dominant eigenvalue is actually negative, which means that if that is the case, that there might be, a damped oscillation, but that oscillation will damp out, or it might just be an attractor where the trajectory goes directly to there. And then, of course, we will do in class through numerical simulations. I just want to show you here, it looks pretty complicated, as you can see, but this is the type of graph we'll derive together, where I have plotted the isocline of the prey in green, the isocline of the predators in red, and trajectory for different initial conditions, and also those arrows represent what is the direction where the system is moving if it is in any of that point of basically this state space. So the things that basically we know and we learn here is that a prey-predator Lotka Volterra model for a Malthusian prey basically show that the predator can control the prey, but this specific system is characterized by sort of a neutral equilibrium, in the sense there are infinite cycles that depends upon the initial conditions. So that actually really the best model. So our next step is to see how we can change this model to get something that potentially closer to observation. Okay.